Welcome back. On this part of the lecture, we're going to go deeper into the calculations we do for equilibrium concentrations. So these are the two objectives we have been working on. Calculate equilibrium concentrations given the equilibrium constant and all concentrations in equilibrium except one. So we have already done that one. That's the one that we did using stoichiometry. Is you knew one of the equilibrium concentrations using stoichiometry and the fact that the reactants are being consumed and the product is being created, we were able to find the relationship and we were able to fill up the ice table. What we're doing now is the one that is going to involve the quadratic expression. This is the one where we're going to be calculating the equilibrium concentrations, all of them. None of the equilibrium concentration is given. The only thing given is the equilibrium constant and the starting concentrations before they reach equilibrium. So let's see how we are going to do that. So we're going to see it with this problem. If you have a flask of a volume of 1 liter, and you have 1 mole of hydrogen gas, therefore you have 1 molar, 1 mole divided by 1 liter, and 2 molar iodine gas. This happens to be at 448 because the equilibrium constant, the same as the rate, changes with temperature, so you got to specify the temperature at which you're working on. We are given the equilibrium constant, so we can see that this is bigger than 1, so this is a reaction that favors the product, so it's going to give you a lot of products. And he's asking, so given those two initial concentrations and the equilibrium constant, what would be the equilibrium concentration of each one of them plus the new product once it reaches equilibrium? Basically, what remains on the flask after equilibrium has been reached. And here's the equation we're dealing with. So once more, we're going to be doing an ice table. So initial, the change, and the equilibrium. So that's what we call it an ice table. And the problem is telling us that we began with 1 molar of this, 1 molar of that. That was at time 0, therefore there was no product at all. We know that the reactants are being consumed. That's why we put the negative there. And we're going to say that an X amount is being consumed. Since this is 1 to 1, you got the same X or the same amount for both of them. However, this is 2 to 1. So for every 1 mole of H2, you produce 2 mole of HI. For every 1 mole of iodine, you produce 2 mole of HI, or hydrogen iodide. So therefore, there's a relationship of 2 to 1 for the product. So that's what you have plus, because it's being created, it's being produced, and it's twice as much of what you're going to consume of that. So we're not consuming the whole 1 mole that we put there. We're only consuming a portion of it, which stoichiometrically is the same one as the other reactant. And stoichiometry tells us that this is going to be twice as much. So what would be the equilibrium concentration? Where would be the initial minus the change. So the initial minus the change. So this is my equilibrium concentration for the first one. So whatever remains, so basically on Chem 1411, you will call this the excess that remains. The same for iodine. You begin with 2 molar, you consume X amount, so obviously you're gonna have 2 minus X left at the end. And for the product, initially you began with nothing, but you produce twice as much of the other reactants. So at the end, that's what you're gonna have equilibrium concentration. So you were able to express the equilibrium concentration But all you have to express it with is a x, unknown amount. We're just using stoichiometry to build a relationship. So you know, based on x, you know how much hydrogen gas remains at the end in equilibrium. You know how much iodine remains at the end, and you know how much hydrogen iodide you were able to create. So that's the best thing you have in terms of numbers, x's. So what we're gonna do, we take the equilibrium concentration expression and we fill it up with those values, hi to x, h2 and I2, 1 minus x and 2 minus x, and that's what we put in here. But now you have to consider also that there's some powers involved. So that power have to show there. And we know that the Kc, because it was given, right? The Kc is 50.5 of the equilibrium concentration, constant based on concentration. So now at this point we're done with the chemistry. At this point it's a math problem. So you know how to deal with polynomials and so on. You're supposed to know that. If you don't, I'm not gonna cover it here. Come to my office, go to the Science Learning Center, go to the tutorial videos and anything you have to do. So we're focusing on the chemistry. So what you're gonna do, you're gonna expand the expression. So doing what you already know about dealing with polynomials, you come up with that quadratic expression. And now that you have this quadratic expression, because you expanded the concentrations that we figure out based on the chemistry we know, now you just use the algebra and you clear one of the sides, this multiplied by this, and that gives you that, and then you expand this, and that gives you that. Now continue going to the quadratic expression, which is going to be equal to 0. So move this to that side, and you come up with this form of the expression. So like once more, I know it sounds rough. This is the math that you should already know based on the prerequisites. So we're not putting too much time on this, but you can see it step by step on the book or the tutorial videos. So the important part for us is that you came up with a quadratic. And a quadratic, we can get the value of x by using the quadratic expression. And this is the quadratic expression. So you came up with this after doing all the math that you know how to do. This is A, this is B, and this is C. And then just fill up the quadratic expression. When you do that, you're solving for x on this case, based on the quadratic expression. You got all your values divided by this. Now it's just a matter of putting everything on your calculator. And since this is a quadratic expression, it's going to give you two values. And at this point, this is where we go back to chemistry. So now that you did the math, you have two values. And what do I mean with this is where we do the chemistry? Well, let me show you. So these are the values that the math gives you. Let's go back to the original problem. When we go back to the original problem, we know that our concentration is going to be this. And what did we get from the quadratic expression? Oops, wrong one, sorry. So let's go back to the values we got from the quadratic expressions. So those were those values in there. And when we go back to the actual chemistry, this is what we have. We have a molarity of 1 minus x. That should give us the concentration that remains. If this is the value, you're going to do 1.00 minus 2.323, and that's going to give you a negative molarity. That makes no sense. Molarity is something that you can actually see, you can actually measure. Being a negative value doesn't make any sense. So every time you do the quadratic expression, you're going to get two values. Then you have to think about the chemistry that you're doing. This value makes no sense. This one does work. So 1.00 minus 0.935. 10 minus 5 is 5. 9 minus 3 is 6. 0. 0.065 molar is how much remains of the hydrogen gas. How much remains from the iodine? 2,000 minus 0.935, 5, 6, 1.065. So 1.065 is what remains of this one. And how much was created? 0.935 multiplied by 2, 10, 7, 18, 1.87 molar. And I bet you, if you take those values, and you put it on this expression, I bet you're gonna get 40.5. So let's pick those values again. Let's check it over here. Oops, sorry. So HI 1.870 to the square. Hydrogen gas 0.065 multiplied by 1.065. When you solve those numbers, you better get 50.5, unless I did something wrong on my mental calculation. So that's the whole idea of this. By using a lot of math, are you able to find the equilibrium concentrations for this particular reaction at this particular temperature? So once more, the most important part here is to recognize the stoichiometry involved on the problem, to realize that the reactants are being consumed, so they are decreasing. Since you have a coefficient of 1, that's what you have, 1x, 1x. The product is going to be created proportionally to that, so 2x, and it's being created. And that's the change, so initial minus change gives you the expression for the equilibrium concentration. And after that, it becomes a polynomial problem, an expansion, you leading into the quadratic expression so that you can find the two values that any quadratic expression will give you, but one of those values is not going to make sense. So you have to eliminate the one that doesn't make sense by recognizing that you can never have a negative molarity in equilibrium. A negative molarity doesn't make sense. And this is what we just did. Multiply by 2. So here's your daily work. The answer that you should get is this one. So when you work on it, if you did all your math the right way, that should be your answer. If you struggle a lot with the math, by all means, come to my office so I can work with you one-on-one. Go to the Science Learning Center, make an appointment online with the 24/7. You can also make an appointment online with the Science Learning Center. Go to Alex and look at the explanations, or go to the textbook where you can see everything done step by step, neatly explained. So please let me know if you have any problem with this. Bring it to the workshop if we really want to work on this, on the math part. Another problem. For the reaction with an equilibrium constant of 0.513, so this one is less than 1, so this reaction doesn't produce too much product. This is going to favor the reactants. Less than 1 means the denominator on the expression is the biggest one, which is the reactants. If the reaction vessel initially, so we're doing the ice, contains N2O4 concentration of 0.004 molar at 500, so that's what we have initially. And initially, the reaction hasn't started, so the product is definitely 0. And we're still looking for the equilibrium concentration of both the reactant and the product, because remember, this reaction reaches equilibrium, so the reactant is never consumed 100%. And equilibrium expression will be this, and we're giving the equilibrium constant. So once more, the change is going to be, the reactants are going to be consumed while the product is increasing, is being created. And the relationship between this is 1 to 2. So for every X amount that is consumed, you're going to create 2 times that amount of the product because of the stoichiometry of this reaction. And then we do equilibrium. Equilibrium is nothing more than initial minus the change, which gives you the equilibrium concentration. And the best we can do is to express it mathematically with a X value, and then you get your product. And now all we have to do is plug the numbers where they need to go, considering that there's going to be some factors in there. So let's do that. So we plug those values in there. And then we expand, multiply that by that. That gives us this. And then move this to the inside, so you have 0 at the end. A quadratic expression has to be equal to 0. That gives you this quadratic expression. And then we apply the formula for the quadratic expression, which is right here. So that would be the formula for the quadratic expression. And you know you don't have to memorize that. That will be given to you on your formula packet. Apply the quadratic expression to give you 2 values. And your 2 values are going to be these 2 values. Based on the expression here, 0.0500 minus x, we know that this one will make no sense, because it's telling you that the concentration was negative. Remember, x is a molarity, so this cannot be negative. So this is the only value we can use, 0.0385. That will give us the concentration of the reactant, and the concentration of the product at equilibrium is going to be 0.0385. So that will be that, and that will be that. When we put it back, so how can you double check that you did everything right? You put it back into the expression, and you better come up with the equilibrium constant that was initially given to you. It has to give you that number. If it doesn't give you that number, you did something wrong on the math. During the test, Write everything down, because if you do something wrong on the math, and I can see that it's a math problem, you're not going to lose that many points from it, as long as I can see that you're doing the process right. But you should be able to tell me, I don't know what I did wrong, but I know this should be the same number, but I couldn't get it, and I ran out of time. If you do that, you're good, because I know you know the chemistry. If you press on without even noticing that it doesn't match, you lose all the points. Show me that you know the chemistry. And this is your daily work. So basically, a little bit more practice of the other one. Only difference on this one, we're doing KP, so we're dealing with pressures instead of concentrations. And with that said, this was done on the previous recording, so this is what we were just doing. We were calculating equilibrium concentrations, right? The ice table, the bottom row, and we were giving the equilibrium constant and only the starting concentrations. That's what we had to do, so many minus x or plus x, and then we had to use the quadratic expression. So with that said, we move into a new concept, the Le Chatelier's principle. So not much math on this one. This is very conceptual. So what does the Le Chatelier's principle tell us? Once a system reaches equilibrium, it will remain in equilibrium unless it's disrupted. If the equilibrium is disrupted, nature will do whatever it needs to do to get it back to equilibrium. So let's see how we're going to do that. And we're going to see what are going to be these disruptions? The disruptions are going to be changing the concentration, like adding something to it or take something out, changing the volume, changing the temperature. We're going to see that that's going to affect the equilibrium position. Changing the concentration, this is something I did when I was doing my graduate research. That's a very powerful technique to get a reaction to happen. Because I told you before, if my equilibrium constant is less than 1, it's not going to favor the products. However, by using the Le Chatelier principle, as I make the product, which is going to be a little bit with something less than 1, if I remove the product out of the system, the Le Chatelier principle will tell me that it's going to try to replace it to get it back into equilibrium to that amount. So by removing the products as I make it, I can force a reaction that doesn't want to happen because it will continue producing the product to try to reach equilibrium again. That's a very powerful tool to know. And all that is based on the Le Chatelier's principle. And we're going to talk about that on our next recording. So when we come back, we're going to be talking about the Le Chatelier's principle, and we're going to see how we can use that. So until the next, see you soon. This part E is going to be our last section for chapter 16.